So let's start with the IV characteristic. IV characteristics of long versus short channel. So it's very important to understand what is a long channel and what is a short channel. So long channel is, as indicated by the name, which has a large value of L or channel length. So those are the transistors that were built in the initial days. But the modern transistors, which are 100 nanometer and below, they are termed as short channel transistors. Okay, so the long channel transistor have a characteristic curve of VDS versus IDS as this, that the current saturates. So you see this flat kind of ID versus VDS curve. But the short channel on the other side, it has a characteristic curve in which the curve does not saturate, but it has a slope. It has a finite slope, which means that in the saturation region, if you increase VDS a little bit, you will see a corresponding change in the current ID. Okay, so there are two explanation or theories for that. One is called the square law theory or square law MOSFET, and the other is called velocity saturated MOSFET. Basically, these two are models that describe the IV characteristic of transistor. So the square law model is useful for describing long channel MOSFETs, while the velocity saturated model is useful for describing short channel MOSFETs. In one case, in the case of square law device, ID is proportional to the square of VGS minus threshold voltage, and in the velocity saturated, it is just related to VGS minus VT. So these are two important models for describing the IV characteristic of transistors and when they are applicable. Now, as you already know, that we have two sort of regions. The first region is the linear region, in which the transistor acts as a gate control resistor, and in the second region it is called the saturation region, in which the transistor acts as a gate controlled current source. Okay, so we want to describe the IV characteristic in terms of an equation. So we want an equation for the ID versus VDS curve in both linear and saturated region. Okay, and we will develop sort of two different equations, one which will describe the linear region and the other in which we will describe the saturation region. And in the other in the upcoming lecture, we will connect the two in the smooth region. So this smooth region, okay, so ideally we want an equation, a single equation that describes the whole IV characteristic, whether it is the linear region, whether it is the saturation region or the smooth region between. We want a single equation. But as a first step, we will see the development of two equations, one in the linear region and the other in saturation region. So let's start with our discussion, and in this discussion the energy band diagram is quite useful. There is some mathematics. I will try to not go into the details of mathematics, but rather focus on the understanding and meaning of equations. So if we consider a MOSFET, for example, on the left hand side, where VGS is applied that is greater than VT, then we know that there will be a channel, and that channel is developed below the silicon dioxide. And if you are interested in what is the charge in the channel, so it is proportional to minus Cox times VGS minus VT per centimeter square. Where it comes from, as we know that Q is equal to CV. This is a well-known equation from capacitor. So this is this equation that for this capacitor, you see the capacitance is represented by the silicon dioxide layer Cox, and the potential difference between these two sides is VGS minus VT, and a negative side sign is because the charge represents electrons. So we do know that when we apply a non-zero VGS, the barrier goes up, goes down from a potential hill to a lower potential hill. Okay, so this is the equation. This is one equation which will be used in the development of ID versus VDS curve. So we also know that the equation of, for example, electric field. So this is electric field. So electric field, it was voltage in the channel, which is VDS divided by the length of channel. So this is the voltage in the channel. Okay. Now, as we know that current is charge per unit time, we can also write it as charge times velocity. Okay, we can also write as charge time velocity. So we can write an initial equation in which ID is equal to charge in the channel, which is Qn, times velocity in the channel of electrons. Remember that this velocity is due to the electric field. The electric field accelerates or carries or pushes the electrons in the channel. So, and the W is the dimension of the MOSFET. And if you remember, we said that the current ID is related to the width of MOSFET. If you increase the width, the current will increase. So this is the overall equation from which we will start, and we will try to insert VDS in this equation. So these are some other equations that we saw in the earlier slide. So one is charge is equal to minus Cox time VGS minus VT. The other is that when there is no potential, when the gate voltage is 0, so there is no charge in the channel. This is the case when the MOSFET is off. Okay, and then this is another equation that comes from the capacitor internals. So it is K0 times epsilon naught by X. So this is how you determine the capacitance of silicon dioxide. Basically, this comes from the physics of how capacitor works. So we insert those quantities into the curve, into the equation. So this was, for example, equation 1, and we insert this channel charge and the velocity and this electric field here, and finally if we insert all these things, we will get this equation. Now this is an equation that describes the current ID in terms of VGS minus VT and in terms of VDS. And in which region? This is the equation for linear region. So you see the equation is related to the width and length ratio times the electron mobility. This is the electron mobility. This is another quantity that comes from experimental analysis, and Cox is the capacitance of the oxide layer, VGS minus VT we know, and VDS. So this is a very simple equation which you can use to describe the current in the linear region. So what is mobility and effective mobility? The mobility of carriers in a channel of MOSFET is often called effective mobility. Why it's called effective mobility? Because it is lower than mobility of electrons in bulk silicon. Bulk silicon means silicon with no impurities. Okay, so here is for example an example in which the mobility in the bulk silicon is 1360 centimeter square per Vs, and in a doped one it drops to 200 to 300 centimeter square per Vs. So the lower mobility is due to basically the surface roughness, of oxide layer. So the oxide layer is not smooth, it is rough, and when the electrons flow in channel, some of the electrons are scattered around. Okay, so that's why the mobility is lower than the mobility in a pure bulk silicon. So now we describe the second equation, which is related to the saturation region. Okay, and we can describe it in two ways. We can describe it with classical pinch-off model. Okay, this is the first one, and we can describe it as a velocity saturated model. So let's see. Now the saturation region is characterized by this property of VDS and VGS, that we have a high VGS and a low VDS. Okay, so for example, for high, I think there is some typo here. I think this should be high VDS. Let me check out this. I think this should be high. Okay, it's okay. So we can say that. Let me remove this. So we start with this situation. So what happens if we start with this situation? If we have a high VGS that is applied at the gate voltage, for example, a high VGS should be VGS is equal to VDD. Okay, and we have a low VDS that is here. Now if you remember that when you apply a non-zero VDS, the Fermi level EF goes down. So you see the source side Fermi level and the drain side Fermi level, they are at different potentials, and you see this kind of shift of in the shape of energy band, conduction band. Okay. Interestingly, you will have a charge in the channel because VGS is equal to VDD. So you have a channel that is created, and the channel is given by this formula, which is here not in the channel at why this is called x naught. This is our we make this point our reference point. So x naught is our reference point, and this reference point is called virtual source. This reference point is important because this simple equation that charge in the channel is equal to Cox times VGS minus VT. This equation holds there. This equation holds at x is equal to 0. Okay, so this is our reference point at which the charge in the channel is for sure Cox times VGS minus VT. And normally the designers of MOSFET, they ensures that this equation holds. It is very important for them to design the transistor in a way that this equation holds at the virtual source. Okay, so we start with developing for the equation of saturation region with a very high VGS, which is equal to VDD, and a low value of VDS. And the channel looks something like this. It looks like the channel is sort of uniform. Channel looks like it is uniform. Now, what happens if we increase the VGS from a low value to a very high value? Now, this is very interesting, that the channel becomes sort of non-uniform, or we say the channel pinch off. Now this pinch off is the reason why the ID saturates in long channel MOSFETs. So this is the reason why ID saturates in the long channel MOSFET. So you see that when you apply a very high VGS, so VDS, so very high VDS on this side, then you can say that there is a sort of position dependent potential difference in the channel. So we have a potential difference in the channel due to this high VDS that is position dependent. What that means? That near Vx is strong near drain, and as you go out towards source side it drops. So our equation for charge in channel now should include another term, that is this potential Vx, which is a position dependent potential of the bulk, and it is subtracted from this. So at exactly this point, this is denoted by Vx pinch, the voltage becomes VGS minus VT. Why that become VGS minus VT? Because this is the value. If you put this value in this equation, then it will become, resultantly the charge in the channel at the pinch off point becomes 0. So this is sort of very confusing. because the current ID is not equal to 0. But from here, the charge at the pinch-off point is 0. It's actually not 0, it's very near to the 0. Okay? And what happens actually is that the electric field near the pinch-off point is very strong, and the number of charge or the charge carrier is very low, but the electric field is very strong, so it moves through the pinch-off region very fast. So overall current is charge per unit time. So though the charge is very low, but the velocity or electric field is very high, so the overall charge per unit time is the same. So it is the same throughout the channel. Okay, so you have to understand this, that although charge is nearly 0 near the pinch-off point, but the current throughout the channel is constant. And why it is constant? Because at the pinch-off point, the electric field is very strong and the current moves very fast in the pinch-off region, and overall charge per unit time is the same. So this can be better understood with the energy band diagram. So you see, this is the conduction band for the case when the drain voltage is very high. Okay, and we are in the pinch-off region. This is for long channel MOSFETs, and this is for short channel MOSFETs. Okay, so in the short channel MOSFET, you cannot clearly see the pinch-off region sort of disappear. You can only see it in the traditional old long channel MOSFET. And one reason is that you see the shape of the curve. It's something like this. This is the pinch-off point. So you see that after the pinch-off point, you have a potential valley. Okay, and when the electron comes here, it goes here with very high velocity. So that was what I mean by a very strong electric field. Okay, so again we can start with the equations. I don't want you to derive the equation exactly, but let's try to understand. We start with the same formula for ID, which is charge in the channel times the velocity. Now we start with the virtual source. So we start at the virtual source, and at the virtual source we know what is our charge, we know what is our velocity. Okay, so it all in all these equations, the x is equal to 0. We also know the electric field. Now the electric field is different compared to the linear region. It is minus Vx pinch off divided by L, and V pinch off is basically minus VGS minus VT. So we put all these into the equation and we get this equation, which is the equation of ID versus VDS in the saturation region. One thing is that in this equation we have this 2, but we have to understand this 2 comes from some mathematical manipulation, but overall you see that ID is proportional to VGS minus VT whole square. So remember the square law model. So this is the square law model, that due to pinch off in the saturation region, the current saturates, and it is described by this formula. Okay, so this is the square law MOSFET, and we have both the equation. This is the equation for linear region, this is the equation for saturation region, And what happens in this region is we haven't gone through this, but we will come back to it in the next lecture. And on this slide we have the ID versus VDS curve for short channel modern MOSFET. So you see that the current does not saturate, okay, and in this region the ID saturation is basically VGS minus VT, okay. So in order to understand velocity saturation, we have to understand that velocity is equal to electron mobility times the electric field. So UN is the mobility and E is the electric field. So here is a curve. On the x-axis we have the electric field, which is volts per centimeter square, and on the y-axis is our velocity, which is centimeters per second. And if we plot the curve of electric field versus velocity, we get a curve like this, okay. So in the initial stage, okay, when you increase the electric field, the velocity increases, but there is a point at which the velocity saturates and you cannot increase the velocity beyond that point. So interestingly, if you calculate the electric field for a modern short channel transistor, the value of VDS is typically 1 volt and the channel length is for example 20 nanometer. There are transistors whose channel length is below 20 nanometer. So you get this 5 into 10 raised to the power 5 volts per centimeter. This is a very strong electric field, okay. Inside the channel. So you see it's a very strong electric field inside the channel, and as the channel is very, very short, it is constant throughout the channel, okay. So this explains why the pinch off does not occur. So the velocity saturates at a constant value and you see that there is no saturation. So this is, for example, the characteristic curve for a 100 nanometer transistor, and if I want to derive the equation, you see that the electric field is greater than 10 raised to the power 4. It was 10 raised to the power 5 volt per centimeter square for L is equal to 20 nanometer and VDS is equal to 1 volt. We calculated this in the previous slide. So electric field is very, very strong and it is constant because the channel is very short. And again, if we start with the same formula, so we can put the charge, we can put the velocity is velocity saturation, and all these things gives us this equation that ID is equal to W times Cox Vsat VGS minus VT. So this is the equations that explains the saturation region in velocity saturated model. So we can combine the two equations, and on one side we have this equation. This is for linear region, and on the other side we have this equation this is for saturation region. Okay, you see there is no square term. Okay, so in the velocity saturated model, which is used for modern short channel transistor, there is no square term. Okay, so this is some let's say simulation which shows how the velocity changes with the position inside a channel for more recent modern transistors. Okay, but let's go over this. So there, what this slide shows that there can be a situation in which velocity is not constant. What that means that there are exceptions to velocity saturation. Okay, so modern research shows that there are exceptions to velocity saturation. For example, the velocity used to saturate at this value, but now due to some reasons which we do not want to go into details, the profile for velocity is something like this. Okay, it is not constant inside the channel because of scattering and different kinds of phenomena. So we come to a piecewise linear model. So we say that one region is described by this equation and the other region is described by this equation, and basically there is a certain magical voltage VD set which is equal to this value. So if you are below this value, you have to use equation 1, and if you are above this value, you have to use equation 2 in order to calculate the current. So this is a piecewise linear model, but we want a model that is more, it's not like this, but is rather smooth here. Okay, and we will come back to this thing. So again, this is just a repetition. We have, for the square law theory, we have this equation in the linear region and we have this equation in the saturation region. Okay, and let me stop here